Okay, in this video I'm going to look at using VSEPR to look at the shapes of molecules, and then we'll use that to predict whether or not these molecules are going to form dipoles or not. So recall, to form a dipole, a molecule needs to have two things going for it. First of all, it needs polar covalent bonds. How do we check if it has polar covalent bonds? We look at the electronegativity difference between the two atoms, and we want that to be in the range from 0.5 to 1.7. If it's below 0.5, we say that it's a pure covalent bond and the sharing of electrons is not uneven enough to warrant it forming a dipole. If it's above 1.7, we say that the electron is transferred, and so we call that an ionic bond. So let's look at our first molecule here, SO2. So first of all, we'll do our electronegativity difference. Oxygen's electronegativity is 3.44. Sulfur's is 2.58. And so our difference here is 0.86. That's squarely in our range, so we're happy. So far we have polar covalent bonds. And the second thing that we need to make sure of is that it has an asymmetric shape. If the shape is perfectly symmetric, then we can imagine that these dipoles pulling in all the different directions might cancel each other out. So now I'm going to do the Lewis structure of this SO2 and see what shape it takes on according to my VSEPR chart. So S, O, O, and then I'm going to count electrons. 6 from my sulfur plus 2 times 6 from my oxygen gives me a total of 18 electrons. Octetting everybody. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I still have too many. I'm going to form a double bond here. Okay, so that's my Lewis structure for this this sulfur dioxide. Now, let's see what shape that's going to take on. So I've got 2 bonding sites for electron and 1 lone electron pair. So 2 bonding sites plus 1 lone electron pair means that this is forming a bent shape with a 120 degree bonding angle. Oh look, it's the example molecule for this. So what that means then is what this looks like in real life is sulfur double bonded to an oxygen and another oxygen and a lone electron pair, 2 lone electron pairs and 3 lone electron pairs. What we can see based on this triangular shape is that it is indeed asymmetric, which means that any polarity that's created by these polar covalent bonds will not be able to cancel out, but instead will be unbalanced. What that means then is since sulfur is the slightly less electronegative ion, it will form a dipole of partial positive, and the oxygen, as the higher electronegativity atom, will attract those electrons a little bit more and make a partial negative. So since we have our polar covalent bonds and we have an asymmetric shape, we say a dipole is formed. Let's look at another one here. Now we'll go very slightly differently to SO3. Octetting. Now counting electrons. 6 plus 3 times 6 is 24. Oops, I didn't restate this. I'm still dealing with sulfur and oxygen, so I still have my electronegativity difference of 0.86, and so I'm still dealing with polar bonds. I didn't think I needed to repeat that part because I did it for the last one. Okay, now 24 electrons. How many electrons do I have? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Too many? I'll make a double bond. There we go. There's my sulfur trioxide. Now let's look at this on our VSEPR chart. We see we have 1, 2, 3 spots bonded electrons and we have no lone pairs. So we have 3, and 0. So we're dealing with a trigonal planar, or something that looks like BF3. So it's actually kind of drawn right already, where it's in a triangle where these are 120 degrees each. Now this shape, being a perfect triangle, is symmetric. So what that means is these oxygen atoms are all going to pull on these electrons, but they're all pulling with the same strength in completely opposite directions. So if we might imagine the giant tug of war over those electrons, no one's winning it, and as a result, no dipole forms. So we had a dipole here, but due to our symmetric shape with SO3, we get no dipole, despite the fact that we still have polar covalent bonds. One more example, H2S. H2S, we might look at that quickly and realize S is in the same column as oxygen. So H2S is basically going to look exactly like a water molecule. In fact, this is the correct Lewis structure for it, with 2 bonding sites and 2 lone electron pairs, or the characteristic angular or bent shape associated with water, where this bond angle is 104.5. Now within that, we see that we have an asymmetric shape. So we might be thinking a dipole is going to form, but let's slow down and check our electronegativity difference and make sure that we had a polar covalent bond in the first place. So here's sulfur at 2.58 and hydrogen at 2.2. So 2.58 minus 2.2 is going to give me an electronegativity difference of 0.38. That is not big enough to get us into the range that we would consider this to be a polar covalent bond. So this is a non-polar bond. So remember, to form a dipole, you have to have both of these things. You have to have a polar covalent bond and asymmetry. Here we have asymmetry, but we don't have the polar covalent bond, so once again, no dipole forms. So there's just a few examples. You should get used to using this chart and looking at whether or not dipoles form so that we can predict what the main type of intermolecular force that might exist with the molecule is, and then as a result, the physical properties that that molecule would exhibit based on that.